Okay, thank you for the introduction. I'm very glad to present our paper, Personalized Motion Retargeting through Bidirectional Human-Robot Imitation. And human-to-robot motion retargeting is very essential now for how to teach robot to learn skill in an efficient way, and also very important for the social robots. And the existing methods mostly focus on predefined similarity metric, or just human annotated some data set to learn from. And inspired by this study in psychology, this study basically says study on the infants. Basically, the study shows that infants will improve or boost their imitation learning ability when they are imitated. So good parents not only let baby to imitate them, they also imitate their baby to give the feedback to improve their ability. So how to bring this idea to teach robot to improve robots' imitation ability? So we introduce this bidirectional imitation. So first, show a demonstration and the robot imitate a human. Maybe there's not perfect, and then the human imitate the robot with the current pose. And with this feedback, we try to formulate an incremental learning method and try to refine the robot imitation performance. And our current method is extension of our previous method, imitation night. And this method, I will quickly talk about it. It's a learning-based method for motion retargeting. It translates poses from a human pose to robot pose, and it learns a shared latent space between different embodiments, which in this space, similar poses are placed closer, and dissimilar poses are far away. And this method is, like I mentioned in the motivation, is based on the similarity metric. It defines a rotation-based similarity metric, just measure the body limbs, and to calculate a similarity score between two poses, no matter from human and robot. During training, it has 3 components. One is a human encoder, and encodes the human joints into the latent space, and another is the robot encoder mapping between the robot joint space to the latent space. It has additional robot encoder which maps the latent space back to the robot space in order to generate robot motion. And this is learned with a lot of human data which is random, and a lot of robot data which is generated by forward kinematic. So there's no pair data required, and they use this similarity metric with this contrastive learning technique and to learn this space. I will quickly show some results to show this space is smooth and in high quality. To show the result, I randomly select the 3 points in the space, and then I do linear interpolation between 2 poses, and then I decode everything to the robot pose. And you can see, even through linear interpolation, it will generate a smooth robot motion. And I also show some qualitative results from this method. During the inference, it just used a human encoder and a robot decoder and directly bridged by the latent space. And it runs very fast because the model are implemented as an MRP. It can run in 1000 Hertz on CPUs. And extension on this method is a similarity metric based, but very simple similarity metric or this rotation-based similarity metric cannot really cover human expectation on the imitation. For example, it neglects the body shapes, and for example, also body context is very important for human to express some special pace. For example, if you want to touch your head, which has some special meaning, but with only rotation-based similarity metric, you will see probably the robot his hand is far away from his head. Or there's a selfie pose, you want to put your hands close to your eye. Such user-specific postures is not easy to describe with some simple similarity metric. So to improve the performance on this more user-specific motion retargeting, we introduced this PMR, the personalized motion retargeting, as a continuous framework. But first, it uses imitation net as a basic motion retargeting method. Here, I show this simplified methodology. And then the human gave a demonstration and goes through this motion imitation net, and then the robot imitated the human. But you see, it does not satisfy the user's expectation. And then the user can imitate the robot and then encode back through the human encoder to the latent space. And from the human feedback, we can see there's a discrepancy between the human's expectation and the rotation or the similarity metric. So, of course, we have a constraint to minimize this discrepancy, like these 2 points are close to satisfy the human's expectation. But if we only have this single constraint that move 1 point to the other point, then we will violate the continuity in our latent space, as I showed the result before. And then we decide to have a local region, like a remapping subspace, is centered at the where the human want to correct. And in this region, we do similar as imitation net. We use the large scale data set to do the contrastive learning, to learn it, to make it smooth. And in addition, we also expand this space a bit larger. We call the transition subspace, because we want to move this, update this remapping subspace, but we want to keep the rest of space unchanged. So in order to make this smooth transition, we expand this space, and how to ensure that the rest of space is not changed when updating the network, and then we have another loss to fix, to constrain that the current network is the same performance as the previous network in the other irrelevant region. Overall, we introduced 3 regions. One is like update region, where the user have the feedback, and then we have a transition where to ensure like a smooth transition between the update region to non-update region, and we have 3 losses. And we implement this as incremental learning, so we let the robot to human to interact with the robot with a very quick, fast responsive time, and then they can do very fine-grained correction. Here I give an example to roll this out. You see that first, the robot imitated the hand is far away from its eyes, and then it learned from the feedback from the human, but it overshoot. The hand is too low, and the human imitates once more, and then in the third round, it can already achieve visually very promising results. And we ask 3 users to perform 4 motions, and then we evaluate. We let each user to annotate their own pose, the ground truth, and then we evaluate the MSE error. This is our get result, and then this is a detailed result on these 4 motions. And then our conclusion that we introduce this learning-based personalized motion retargeting method to refine the motion retargeting based on the human feedback. And our framework is very responsive, so it can, in each iteration, only 25 seconds. And yeah, also evaluate on 3 participants. Thank you very much for your attention. I'm ready for questions.
Thank you very much. Do we have questions from the audience? Emre?
Yeah, very nice work.
Thank you.
So we always imitate
Yes.
humans, but now humans imitating robots makes a lot of sense. So what are the limitations of this work?
The limitation, of course, is like when I implement this, is a little bit depends how human satisfied to his satisfied the retargeting. Probably have to do multiple iterations. It depends how many iterations human do. Probably it's a more burden from a human side to really refine this process.
Is it possible to apply some update learning?
We didn't do that. But yeah, I think it's possible to actively explore the space and to try to boost this process. Yeah, I think it's possible.
No, thank you. That was really interesting. So something I'm curious about in kind of the loop you showed. Once the robot is doing kind of what the human would want, like the feedback is good, there's basically a termination, right? Is there any consideration for, as it stands, like can it, I guess, save that motion so that next time, if you say you want a pat on the head, like
Yes, it will save, yeah. If you update its learning and then update all saves.
Thank you.
Thank you.
Another question? Well, I have one. I am always concerned about the effort that it requires to involve a human and give it feedback to the robot. So how close could you bring your system maybe to imitate the original motion, maybe by recording the demonstration, and then only providing feedback at the very end?
I understand that you want always give one demonstration, record at the beginning.
Try to reduce the amount of feedback at the end. So the human imitating the robot, I think is a good step. Then maybe you can find a better alignment between what the human expected. But that is very time consuming if you want to scale up the number of behavior you want to learn. So how close could you bring up the first part?
And the first part you see, this is first iteration, you can see it's like very close, but it's a little bit overshoot or less shoot, depends on it's tuning of a parameter, how many updates. We update 100 steps, so we just take 25 seconds to make it fast. But if you can update more, but it can overshoot, so it's a parameter need to be tuned. Yeah.
Any more questions? No? I would like also to invite the next speaker to move on front, and if you have another question.
We have is there a question?
Just to clarify, the 25 seconds is for the whole process, right? It's just not one iteration for the imitation.
It's a one iteration actually.
Okay.
Yeah, but it's as I said, it's tunable. So we did 100 steps, but in order to let the human do less iterations, it's a trade-off between how human do refine and how you use the human data to update more.
Yeah, okay. And how invariant is it to another person coming in and doing the same pose? Like if you switch the person between between two iterations?
So actually also like this called personalized, because for each, you see we update the human encoder, actually is a personalized encoder for each human, because each human have its own kinematic structure. For each human, it's learn own human encoder. Between humans, it will still beneficial to use from other humans because at least are closer, but still some, I think, less update iteration is you will have a less update iteration if you use other humans at the start.
Okay, thank you very much. Let's give a warm applause to our speaker.